Very good morning to all of you. This is Dr. Divya Bartaria, Associate Professor in Chemistry, United Group of Institutions, Allahabad. I welcome you all to this first session on phase rule. So this is an introductory session, and this session would be basically focusing upon understanding the terms phase, which is represented as P, capital P, components, degree of freedom, and their applications in various systems. So since this is an introductory session, so we will be focusing upon the terminologies P, C and F, and also we will try to discuss their implications. So this first session will be defining the phase rule as well. Today the agenda would cover these important topics, as you can see here: phase rule, introduction part, and then explanation of terms, wherein we will be understanding the terms phase, components, degrees of freedom, and then phase rule, its definition, because in the next session we would be discussing in detail the phase rule. Now when we come to the phase rule, all of us know that what is the term phase is very much important to us, that what do we mean by phase here. So a substance can exist in various states depending upon the external conditions. For example, water can exist in 3 states, you can see here: solid, liquid and gas. So here each of the state is referred to as a phase, and if we are using this term phase, so you must consider the state of matter as well. Now all of you are aware of this term system, so I may take this term as well, because whenever you have studied in thermodynamics as well, that what is a system, then you can say that any portion of specific part of the universe which is under study or experimental investigation is termed as a system. Now a system is divided into 2 categories: homogeneous system and heterogeneous system. So what do we mean by a homogeneous system? A homogeneous system consists of only one phase, that is, it has uniform composition. However, a heterogeneous system consists of 2 or more than 2 phases, and that is why it has non-uniform composition. So friends, dear students, phase rule is an important tool in order to study the equilibrium of heterogeneous system. So that is why we have considered this term system as well, because we have to understand what do we mean by homogeneous system and what do we mean by heterogeneous system. So phase rule's important role is it is used as a tool to study the heterogeneous equilibrium. Let us move ahead. The first important term is phase. Now how do we define a phase? You can see in the slide. A phase is a homogeneous, physically distinct and mechanically separable part of a system which is separated from other parts of the system by definite boundaries. In other words, phase is a state of matter that is uniform throughout, not only in chemical composition but also in physical state, right? So there are certain criteria which are the conditions which should be fulfilled while defining a phase, right? Number 1, a phase must have the same composition in all of its parts, right? Second important condition is that it should be separated from other phases of the system by surface of contact. That is why in the definition also it has been mentioned, it is physically distinct and mechanically separable part of a system. Then the third condition is that the phases of a system are in dynamic equilibrium with one another through the exchange of chemical species. So these are certain criteria which are to be considered while considering any state of matter as a phase. So let us consider few examples. If we consider a crystal of a substance, a single crystal of a substance or any solid substance, then here we can very confidently say that the number of phases will be 1 only. So any specific solid substance represents single phase system. This is single phase system. So if we consider any solid substance, then we can say that it has number of phases 1 only. Now if we consider 2 substances mixed together, 2 solid substances mixed together, so always remember that 2 solid constituents or the substances cannot be completely mixed together. So in any case, we have to consider number of phases here as 2 only. If there are 2 solid substances, then they should be considered as 2 separate phases. So here in this case, you can see that the number of phases should be 2 only. Now let us consider gases. So all the gases completely mix together to constitute a single phase, and that is why air is a mixture of gases, but here the number of phases is 1 only. So all the gases completely mix together to constitute a single phase. So mixture of gases will represent single phase system. So this is single phase system, mixture of gases, right? Now in the next case, we can see 2 miscible liquids are mixed together to form a solution. Let us consider here. Suppose in a beaker we are taking 2 substances or liquids mixed together, A plus B. Now these are miscible, right? So if these are miscible, then they mixed together to constitute a single phase system. So if they are miscible, so P is equals to 1, that number of phases will be 1 here. Now there is another case wherein we can see if suppose these are 2 liquids which are mixed together and it is covered. So there is another phase, you can see that these are vapors of A and B. So this is constituting another phase, right? So in this way you can see if we consider 2 miscible liquids mixed together, then there may be 2 cases. If we consider this particular system only, right, then here you can see that number of phases will be 1, right, P1 and P2 mixed together, right. So both the substances, both the liquids are mixed together to constitute a single phase system. So P is equals to 1. Now in another case you can see if it is covered and now we are considering this system as a whole, then here we have to consider vapors of A and B as well. So that is why in another case we have considered phases is equal to 2, number of phases is 2. Why? 2 miscible liquids mixed together constitutes 1 phase and vapors of both the liquids mixed together constitute another phase. So here number of phases will be 2 only. Similarly, you can consider the last example. Here you can see there are 2 immiscible liquids mixed together. So when 2 immiscible liquids are there, then definitely we can say that the number of phases will be 2 only because they are immiscible. But we consider the system as a whole, then 2 immiscible liquids plus vapors of both the immiscible liquids. Now vapors will mix together to constitute a single phase. So in this particular case you can see number of phases would be 2 when only the solution is considered, and when the entire system is considered, that the number of phases will be 3 only. So here we have considered both the cases, P is equal to 2 and P is equal to 3. Now let us take another example. If we consider saturated solution of water and sugar, right. So here what do we mean by saturated solution? This has to be understood. You have to recall in your memory that what do we mean by saturated solution. Now saturated solution means the solution of water and sugar and some part of solid sugar settled at the bottom. So here it has been mentioned solution of water and sugar, because whenever there is a state of saturation, then whenever you mix the sugar inside the water, then it stops dissolving and we get an unmixed part of the sugar and which settles down at the bottom. So here you can see that the number of phases would be 2. Why? Because solution of water and sugar plus solid sugar settled at the bottom. So in this particular case you can mention P is equal to 2. Now if we consider unsaturated solution of water and sugar, then definitely you can confidently say that P is equals to 1 only, because here there wouldn't be any settled part of the sugar. So here you can see that both the water and sugar mix together to constitute a single phase system. So P is equals to 1 only. Now the third example, here you can see at 95.4 degree centigrade, sulfur exists in 2 crystalline forms, sulfur rhombic and sulfur monoclinic, right. So in this particular case you can see that there are 2 alloys or crystalline forms of sulfur, sulfur rhombic and sulfur monoclinic. So, these represent two separate phases. Why? Because these allotropes are similar in chemical properties, but are different in physical properties. So, whenever we considered two different solids, then also we consider two different phases. And at the same time, here also you can see, since both the allotropes or the crystalline forms are having different physical properties, so they should be considered as separate phases. So, sulfur rhombic and sulfur monoclinic both represent two separate phases here, and they are in equilibrium at 95.4 degree centigrade. Last one. Last but one, here you can see that calcium carbonate decomposes into calcium oxide and carbon dioxide. So, what do you conclude here? How many phases are present here, right? So, you can think over it and you can find that there are two solid substances, calcium carbonate solid and calcium oxide solid, and we have already understood that two solids cannot be mixed together. So, these two solid phases are different phases, P1 and P2, and there is another phase, gaseous state or vapor state of carbon dioxide. So, it should be treated as a separate phase. So, how many phases are there? There are three phases, two solids plus one gas. Similarly, here in this particular case, you can see iron plus water gives FeO solid plus H2 gas. So, here one solid is here, one solid is here. So, these two represent one first phase, second phase, and both the gaseous states mixed together to give only one phase. So, how many phases are there? There are three phases, two solids and one mixture of gases. I hope it is clear to everyone. We have discussed the phase. Now, let us come to the components. How we define the components, right? So, the least number of independently variable chemical constituents in terms of which the composition of each phase present in the system can be expressed either directly or in the form of a chemical equation, right. So, this definition clearly defines if there are many phases in the system, then we can represent the composition of each phase by a single constituent or two constituents. So, the minimum number of independently variable chemical constituents which represent the composition, right, composition of each and every phase is termed as components, right. So, to understand the meaning of component and to find the number of components in a system, some points are to be considered. Let us see what are those points. So, the chemical formula representing the composition of a phase is written on left hand side. The remaining chemical constituents existing independently in the system are represented by chemical formulae written on right hand side. The quantities written on right hand side can be made minus 0 to get the composition of the phase written on left hand side, right. For example, I can show you here, if we want to express the composition of calcium carbonate, so it is written on left hand side, and in right hand side we represent the chemical constituents in terms of which the composition of this phase we are going to represent. So, here you can see it may be CaO plus CO2, right. So, calcium carbonate's composition is represented by calcium oxide plus CO2. So, on right hand side we write the chemical constituents in terms of which the composition of this phase is being represented here. So, here we can have 0, minus, plus and so on. So, we will consider a few examples. On the basis of that we can have a proper explanation. Now, let us start with the simplest example. In water system, what do we find? At equilibrium there are three phases. So, ice is in equilibrium with water and water is in equilibrium with water vapor, right. So, how many phases are there? There are three phases: solid ice, liquid water and water vapor. So, number of phases is 3, P is equal to 3 in case of water system. So, when we talk about the components, so as per the definition, the minimum number of chemical constituents in terms of which the composition of each phase can be expressed either directly or in the form of a chemical equation. So, here in this particular case you can see the composition of ice can be represented or can be shown by, can be expressed by H2O, right? So the composition of ice can be represented by H2O. Similarly, composition of liquid water can be expressed or represented by H2O only. And likewise, composition of water vapor can also be expressed in terms of H2O only. And that is why we can say that a single chemical constituent is required to express or to define the composition of each phase present in the entire system. So we can conclude that number of components is 1 only. So here P is equal to 3, but C is equal to 1. So water is a 1 component system. Similarly, you can consider another example, right? Sulfur rhombic is in equilibrium with sulfur monoclinic. Sulfur rhombic is in equilibrium with sulfur monoclinic. Sulfur monoclinic is in equilibrium with sulfur liquid, and sulfur liquid is in equilibrium with sulfur vapor. So all 4 phases are in equilibrium with one another. Number of phases is 4, right? Why? Because we have already discussed that both the phases may have same chemical properties, but they are having different physical properties. That is why number of phases is equal to 4. But the composition of sulfur rhombic can be represented by sulfur only. Composition of sulfur monoclinic can be represented by sulfur only. Similarly, composition of sulfur liquid can be represented by sulfur only, S only, and likewise composition of sulfur vapor can be represented by sulfur only. So only one chemical constituent is required to express the composition of each phase present in the system. Therefore, C is equal to 1. So it is also an example of one component system. So C is equals to 1 here, right? So here we can see that how we can directly express the number of components present in the system. Now, if we are going to consider the decomposition of calcium carbonate, then we can see that it may be represented as CaO plus CO2, calcium oxide solid, calcium carbonate solid, and carbon dioxide gas, right? How many phases are there? You can see that there are 3 phases, 2 solids, solid calcium carbonate, solid calcium oxide, and gaseous CO2. So how many phases are there? There are 3 phases. It is clear. Now we have to find out the number of components. Suppose we do not know the concentration or the composition of each constituent, so we have to see it in the form of equation. Let us consider that 2 chemical constituents are required to express the composition of each chemical constituent present in the system, each phase present in the system. So let CaCO3 and CaO, calcium carbonate and calcium oxide constituents are chosen, right? So if we consider the composition of calcium carbonate, then considering these 2 components only, calcium carbonate and calcium oxide, CaCO3 plus 0 CaO. So we can use 0 term here. Calcium oxide's composition may be represented as 0 CaCO3 plus CaO. So CaCO3 is represented with the help of 2 chemical constituents. Calcium oxide is represented with the help of these 2 chemical constituents, keeping this 0 here, keeping this 0 here. And now you can see in the third step, carbon dioxide composition is represented by calcium carbonate minus CaO. So here you can use minus entity also, right? So in the second way, we can also use calcium carbonate and CO2. Suppose we are considering these 2 chemical constituents, then also you can see calcium carbonate can be represented as calcium carbonate plus 0 CO2. Calcium oxide can be represented as calcium carbonate minus CO2. CO2 is represented as 0 CaCO3 plus CO2. Likewise, if we consider next 2 constituents, you can also see that how we can conclude that only 2 chemical constituents are required to express the composition of each phase present in the system. Hence, we can conclude that it is a 2 component system, right? So in the form of chemical equation also you can express, you can determine the number of components present in a system. Now let us consider another example, dissociation of ammonium chloride. So ammonium chloride solid gets dissociated into gaseous ammonia and gaseous hydrogen chloride. So the system consists of two phases, solid ammonium chloride and a gaseous mixture of ammonia and HCl, and even vapors of NH4Cl are also mixed together. So, in this way there are two phases present in the system. Now, if we have to find out the number of components, so there may be two cases. One, concentration of ammonia is equal to concentration of HCl, or you can say, in other words, ammonia and HCl are formed in fixed stoichiometric proportions by the reaction. Then both the phases have formal composition, they can mix together to give the formal composition of ammonium chloride. So, these two mix together to give the formal composition of ammonium chloride. So, in this way you can see that this can be expressed by ammonium chloride and this can also be expressed by NH4Cl. So, only one chemical constituent is required to express the composition of each phase, that is solid and gaseous state, present in the system. This is the case when ammonia and HCl are formed in fixed stoichiometric proportions, right. The concentration of ammonia is equal to concentration of HCl. So, they mix together to give the formal composition of ammonium chloride. So, in this particular case C will be 1. Now, in the second case, if ammonia or HCl their concentration differ, or one of the components NH3 or HCl is in excess, then the system becomes a two component system, because decomposition of NH4Cl would not give the correct composition of the gas phase. Hence, either ammonia or HCl would be required to specify the gaseous composition or even the composition of each phase, right. So, X ammonia and Y HCl. So, in that way at least two chemical constituents are required to specify the to express the composition of each phase present in the system. So, here you can see that the number of components becomes 2, right. So, here you can see we can use this formula as well. C is equal to S minus R. C is the number of components, S is the number of substances, and R is the number of independent relations, right, relations. In the previous slide you can see this has been mentioned over here. C is equals to S minus R, that S is this number of substances, R is the relations, equations representing the equilibria, independent equilibria among them, and C is the number of components, right. So, let us move ahead. So, in this particular case also we can very easily find out ammonium chloride ionizes into ammonia and HCl. So, the relationship is 1. So, substances 3, and in that way we can see C is equals to S minus R, 3 is number of substances, R is 1, so number of components becomes 2, right. If concentration of ammonia is equal to concentration of HCl, then relationship will become 2. Why? This is the one relation and this is the another relationship. So, in that way relationship will be 2, and then 3 minus 2 becomes 1. So, it becomes a one component system, right. So, in both the cases we can use this formula as well, C is equals to S minus R. If we consider another example, gaseous mixture of O2 and N2, right. These are two gases, oxygen gas and nitrogen gas. So, when both are mixed together, so you can very easily see that this is the gaseous mixture, right. So, if I find out number of phases and number of components, so the gaseous mixture here, this is the gaseous mixture N2 plus O2, they mix together to give number of phases 1 only. And when we talk about the components, so we do not know the concentration, so X N2 plus Y O2 are required. So, number of component will be 2 only, right. Similarly, Na2SO4 plus water system, right. So, in this particular case wherein you can see that it is a system wherein the crystalline water molecules are present over there, right. So, Na2SO4 dot 10 H2O, suppose Na2SO4 dot 10 H2O, this is the species. Now, it can be ionized into Na2SO4 dot 7 H2O plus 3 H2O. Similarly, Na2SO4 dot 10H2O. This can ionize into Na2SO4 plus 10H2O, right. So, anhydrous molecule plus water molecule. So, in that way, at every stage the number of components will be 2 only. So, each and every hydrate represents a 2 component system. So, you have to remember this. So, if you consider copper sulfate dot water system with water molecules of crystallization, then also you can very confidently say that here the number of components will be 2 only. So, every hydrate has the number of components 2, it is a 2 component system. Last term which we are going to define here, we have defined phase, we have defined components. So, let us come to the degrees of freedom. Now, the degrees of freedom of a system is defined as the number of independent variables such as temperature, pressure and composition which are to be fixed to describe or define the system completely, right. For example, for a given sample of gas, we know that PV is equal to nRT, PV is equal to nRT. So, this example we have covered here. For a given sample of gas, all of us know that there is an ideal gas equation, PV is equals to nRT. So, any two of the three variables, three variables means pressure, volume and temperature, pressure, composition and temperature. So, out of these three variables, only two variables are required to be specified to define the system completely. So, if we fix two variables, then we can define the entire system, and we are talking about the system of any gas, any simple gas, any single phase system. So, in that particular case, you can see that if two variables are required, then the degrees of freedom would be 2. So, it is also known as bivariant system. Degree of freedom is also known as variance of a system, and if the degree of freedom is 1, so it is univariant, if degree of freedom is 2, it is bivariant and so on, right. If we consider water system, in water system also you can see that ice is in equilibrium with water and water is in equilibrium with water vapor. So, how many phases are there? There are 3 phases. How many components are there? There is only one component. This is one component system, but when all these 3 phases are in equilibrium, then no condition has to be specified. This is because the 3 phases of water can exist together in equilibrium only at a particular temperature and pressure, that is the freezing point. So, no condition is necessary to be specified in order to define the system, in order to define this triple point where 3 phases are in equilibrium with each other. So, degree of freedom in this particular case is 0. So, F is equals to 0, or it is also known as invariant system, right. So, monovariant system means degree of freedom 1, bivariant degree of freedom 2 and invariant, that is degree of freedom is 0. Now, if we consider water is in equilibrium with water vapor. So, H2O liquid is in equilibrium with H2O gas, right, or H2O solid is in equilibrium with H2O liquid. So, these two cases represent the case wherein 2 phases are in equilibrium with one another. We will be studying in the next session that these systems are represented in the form of lines or curves. So, here you can see that in this particular case, these two phases coexist along this line. So, if this is pressure and this is temperature, so if we fix the pressure, right, if we fix the pressure, temperature and composition get automatically fixed. Similarly, if we fix the temperature, then pressure and composition get automatically fixed. So, here what we can observe that only one variable factor has to be specified in order to define the system completely. So, if there are 2 phases existing in equilibrium with one another along a line, then only one variable factor, either temperature or pressure, needs to be specified in order to define the system completely. So, in this particular case, you can see the degree of freedom is 1. For a given sample of gas or for a given sample of any state of matter, any phase, the degree of freedom is 2. You have to fix pressure and temperature both. Pressure and temperature both are required to define the system completely, but When two phases are in equilibrium, then you need to specify either temperature or pressure to define the complete system. So today I have tried to give you a basic idea of phase rule and its significance. We have understood the terms involved, phase, components and degrees of freedom, and with the help of illustrations, few illustrations we have taken here, we have tried to discuss various cases in order to find out the number of phases, number of components and degrees of freedom. So dear students, in the next session we will study Gibbs phase rule and its implication to a one component system. So as of now, we wish that you come up with some examples, some questions with respect to the terminologies that we have understood today, and in the next session we will start with some questions, and also we would go ahead with the implication part of phase rule. Thank you very much.